Okay, this is OCR 2021 AS Level Physics, Paper 1, Breadth in Physics. And unlike AQA, I can show this paper on screen because OCR are chill dudes. Okay, number 1, here we go, multiple choice first. Archimedes' principle is written below with one word missing. The upthrust acting on an object in a fluid is equal to the what of the fluid displaced? Well, we know that if something floats, then that must mean if this is an iceberg or whatever, it means that the upthrust going up must equal the weight going downwards, so it is the weight, it's D. 2, which of these is not a source of EMF? Chemical cell. It is, so that's not our right answer. Light-dependent resistor. Oh, well, yes, that's true, isn't it? Because it's just a resistor. That has to be our answer. Let's check power supply. Yeah. Solar cell. Yeah. So they can't be right either. So an LDR is not the same as a solar cell. Similar, but not the same. Number 3, student is explaining the photoelectric effect to his friend. Which statement is correct? An electron is emitted when the photon energy is greater than the threshold frequency. That's not true, is it? Because we have here energy greater than the threshold frequency. So energy and F, they are not the same, so that can't be right. B, increasing the intensity increases the maximum kinetic energy. No, because intensity is all to do with number of photons, not their energy. So that can't be right. C, photons are emitted from the metal during the photoelectric effect. No, electrons are, aren't they? So that can't be right. Has to be D. Let's check it though. The energy of a photon is proportional to the frequency of the EM radiation. Yes. Oh, so that's not really anything to do with the photoelectric effect. That's just photons, isn't it? So we know that E equals HF, so therefore E is proportional to F. Easy start. I'm loving it so far. Number 4. Air resistance F is equal to 0.13 v squared. The mass of the object is 30 grams. What is the terminal velocity of this object? Okay, so what we need to do is rearrange this. So we can say, let's do it one step at a time. So F over 0.13 is equal to v squared. So that means, of course, that it's going to be the square root of that, isn't it? But what is the force? Well, that's going to be equal to, because if you have a skydiver or whatever like that, we know that the drag force or the air resistance is equal to the weight going downwards, and that's our force. So therefore we can say that V is equal to the square root of mg over 0.13. So that's equal to square root of 0.3, 30 grams. Nice one, mate. 0.03 times 9.8. Don't think we need to go to 3 sig figs there. Divided by 0.13. First time using our calculator. And we end up with 1.5 meters per second. So the answer is C. 5. An object is traveling along a horizontal surface with a kinetic energy of this and a speed v. Force acts against the motion of the object. The work done by this force is that. What is the final speed of the object in terms of v? Okay, getting a little bit more complicated. So we know that Ke is equal to half mv squared. So we can just say energy is equal to that. So therefore, this is a proportionality question, by the way. We know this because we don't have a value for v. We're talking about in terms of just v. So we can say that E is proportional to v squared. There we go. We're looking for the final velocity. So therefore, we need to rearrange this to say that v is proportional to the square root of E. Now, there's 2 ways you can do this. We can say that, well, what's happened to the energy? Well, it's gone down, hasn't it? It's gone down by 4 joules. Now, we never care about how much a value has gone down by. We only really care about how much of a value is left. And so therefore, we can say it's gone to, well, it's gone down by a quarter, hasn't it? It's gone from 16 to 12 ultimately because the work done has removed 4 joules from it. But like I said, we don't need that. It's gone to 3/4 of its original value. So therefore we can say that energy is times 3/4. So that means that we're looking for the square root of 3/4. So we can say the square root of 0.75, 3/4 is 0.87. So that is our answer. The answer is B. However, the alternative way of doing this, of course, when it comes to any proportionality question, we can say that, well, we have this up here, so we can say that V1 over V2 is equal to the square root of E1 over square root of E2, or just square root that together. We're looking for, well, it doesn't really matter, does it? So I can swap these round. So V2 on top E2 on top. There we go. Then all I have to do is replace this with our values. We're looking for that, like we said. So therefore, we can say that V2 is equal to the square root of energy 2. We know it's gone down to 12 over 16. And then we times that by, well, just V, isn't it? So we don't really care about that. So we're just looking for the value. And we can see, of course, that there's going to be the square root of 3/4 again. So that is going to give us the right answer. For electrical circuits, all resistors are identical, blah, 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 blah. Which circuit dissipates the least power? Okay, seems like an easy question, but it involves a little bit of thought. You could get caught out with this one. Look at this. They're connected to the same power supply, so therefore they all have the same V. We don't know what's happening with the currents. So therefore, we have to say that power is equal to, we usually might go for I squared R, but here we're going for V squared over R, aren't we? So therefore, if we're looking for the lowest power dissipated, we need the highest resistance. And so that's going to be C, because of course they're all in series, whereas we have some aspect of parallel resistors with A, B, and D. You might have been tempted to go for D. When I just looked at the question, I just immediately went for D because I thought they were in parallel, current's going to be lowest, but no, because we're told they're all connected to the same power supply, it means they're all going to have the same PD. So the answer is C. Not an easy one there. 7. Student investigates 4 different springs, A, B, C, D. Results are shown. All of the springs obey Hooke's law, which has the largest elastic potential energy. Okay, so we have F and we have X, or delta L, whatever you want to call it. So therefore, we're going to use the equation energy is equal to half Fx. So which has the largest elastic potential energy? Well, let's just times these all together, shall we? I mean, we can say that E is proportional to Fx actually, so we don't even need to find the actual value. We can just do F times X, and whichever one has the biggest value is by de facto going to have the biggest elastic potential energy. So therefore 2 times 5.2 is just going to be 10.4. Of course, we know the energy is going to be half that in reality, but we don't care. Maybe we could do that actually. Yeah, let's do that. Let's just use this equation because, you know, maybe it's easy to do. So I'm going to do 1, 2, so I'm going to half all these to get rid of the half from the equation. So there we go. So 2 times 5.2 divided by 2, that just gives us 5.2. Then we have 2 times 4.6, that's going to be 9.2. 3 times 3.5, that's going to be what? 10.5. And we have 4 times 1.5, that's going to be 6. So this one has the biggest one, so the answer has to be C. 8. Which pair of quantities have the same SI-based units? Strain, well, strain is delta L over L, so that doesn't have a unit. So that cannot be true because force constant and elastic potential energy do have units. So let's go for stress. Oh, it's fairly obvious, isn't it? And force constant. Is that what they mean by spring constant? Oh, I don't know. Point is that stress is equal to F over A. The whole point is that Young modulus is equal to stress over strain. And because strain doesn't have a unit, that means that they have the same unit. So therefore D is our answer. Easy. 9. Number density. Oh, number density. Why are OCR obsessed with this? The number density of charge carriers is about this for X and then this for Y. Which row of the table correctly classifies both materials? We know that, well, this one is definitely a conductor here. So it has to be A, right? It definitely can't be B. Definitely can't be C. It definitely can't be D either. It's not going to be a semiconductor. But we're told the material Y here is an insulator. But I was under the impression that, well, this isn't an AQA, so it's just one of those random things in OCR. I was under the impression that charge carrier had to be fairly close to 0 in order to be an insulator. So I'm not sure that that's correct. But A is the only possible answer there. So, well, there we go. It would have to be that just from process of elimination. Number 10, a resistance wire is part of an electrical circuit. Resistance wire is pulled so that it becomes longer and thinner. Oh, great, here we go. Longer and thinner. Okay, so we're going to need our resistivity equation. R is equal to rho L over A. So we know that, well, resistivity is staying the same. So therefore, resistance is proportional to L over A. And we know that if the length is increased, then the area is going to be going down, which then ultimately makes it go up even more. So we know that the resistance is going to go up. Okay, here we go. So what's going on here then? Which statement is correct? The ammeter reading increases. Absolutely not, because we're increasing the resistance of this resistance wire, so that can't be true. The resistance of the wire decreases. That's not true. It increases. C, the total resistance of the circuit remains constant. No, it has to be D. Let's check it out. The voltmeter reading decreases. Yes, that is true because, well, this is a potential divider situation now. If the resistance of this goes up, then therefore its share of the voltage goes up as well. So therefore the share of the voltage across that fixed resistor is gonna go down. There we go. Number 11, monochromatic light is incident on a double slit, blah, 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 blah. Which term together with diffraction can be used to explain these fringes? Not polarization. Look, we know it's interference, don't we? Because it's constructive, destructive interference. That's why we get them. Not polarization, not reflection, not refraction. It has to be A. Easiest multiple choice question of all blooming time. Love it. Number 12, a cylinder of conducting material has a length of that. We have a diameter of that. It has a resistance of that. What's the resistivity? Okay, so let's crack out our equation again. Let's just go for rho is equal to RA over L. That's just the rigid version of the equation we just saw up above. So therefore, we're looking for 24 times, well, we've been given diameter, so area is pi r squared. Yeah, let's just go for that, shall we? We could do pi d squared over 4, but we've been given 2 there, so we might as well go for that. So times by 1 times 10 to the minus 2 squared. That's my r divided by the length, which is 6 times 10 to the minus 2. I guess, well, actually, I can just get rid of that, can't I? I can just cancel the times 10 to the minus 2 on the top and the bottom. Happy days. So therefore, that's just going to be 24 over 6. So therefore, I'm just going to call that 4. So 4 pi, so 4 times 10 to the minus 2 times pi. Or in other words, 0.04 pi. I do not know what that is off the top of my head. Let's have a look. We can see all the numbers are different, so we could just do 4 times pi and just get the number, couldn't we? So that's going to give us 0.0126 ohm meters. So it looks like the answer is A. 13, stationary wave. Frequency of the wave is 72 Hertz. What is the fundamental frequency for a stationary wave on the same string? Well, of course, we know the fundamental, or the first harmonic, is just that. We know that the frequency of this has to be lower than that. It's going to be 3 times lower exactly. So therefore the answer is going to be 24. It's B. Another nice easy one. What a lovely paper so far. 14, de Broglie wavelength of a proton is that many picometers. The kinetic energy of the proton is doubled. Okay, right, not an easy one. Here we go. So we know de Broglie wavelength is equal to h over mv. In other words, h over momentum. Now, we're being told how the kinetic energy is doubling. So how does energy relate to momentum? This is something that people often forget. We know that energy is equal to half mv squared. Let's multiply both sides by m. And so there is, I think you might get this equation in your formula sheet. In AQA, I know it's just in the turning points module part of it. But it's a useful thing to get your head around. So look at this. Times both sides by m, and we end up with m squared v squared over on the right. So therefore, we can say that 2me is equal to mv all squared. So therefore, mv is equal to the square root of 2me. So therefore, taking this down here, we can say that lambda is equal to h over root 2me. And if we know that the kinetic energy is doubled, so it's times in by 2, we know that the wavelength is going to therefore go down by root 2, because this is going up by root 2. So therefore, the whole equation has to be going down by root 2. So 160 divided by root 2, and that gives us 113. So I guess we just round that to 110. So the answer is B. So yeah, kinetic energy and momentum, knowing how to equate those two, knowing how to reconcile those two, very important. 15, space and time graph. Which statement is correct about the phase difference between points X and Y? Okay, so it's basically greater or less than 90 degrees, whatever. So this point and this point are sorry, they're 180 degrees apart. So that to there is 180 degrees. No, this is in the middle, and then, well, therefore it's got to be greater than 180. Yeah. And 270 is, oh, that's 270 there, isn't it? That's 270 degrees, because of course there to there, that's 360 degrees. Yep. So therefore it's going to be between 180 and 270 degrees. The answer is D. What a weird question. 16, energy of a photon is that many electron volts. What is the principal radiation for this photon? Right, we need to find the frequency, of course. So therefore we can say that E equals HF, but we're talking about wavelengths. So therefore we're going to say it's equal to HC over lambda. We're looking for the wavelengths. So therefore we're going to just swap those around. We can say that wavelength is equal to HC over E. So that's equal to 6.64 times 10 to the minus 34 times by 3 times 10 to the 8. Sure, let's cancel some powers. Yeah, let's do that in a minute, actually. Divided by 2.5, but it's electron volts, so that's times by 1.6 times 10 to the minus 19. Yeah, let's cancel some powers of 10. Why not? We've got nothing better to do with our time, do we? So, minus 19 on top, but we're dividing, so we're going to add 19 on top, so that gives us then 27. Minus 34 times 27, well, that's just going to give us then minus 7. So therefore that's the same as 6.63, just write it out again, times 10 to the minus 7 divided by 2.5, and divided by 1.6 again. What does this end up being? 6.63 divided by 2.5 divided by 1.6. That gives us 1.7 times 10 to the minus 7. So in other words, 170 nanometers. So, I mean, hundreds of nanometers, that's basically visible light, so it's C, isn't it? I've got to be honest, do you really need to know your wavelengths? You need to know that, of course, that hundreds of nanometers is standard for light, isn't it? Okay, moving on. 17, student is recording results in a table. Calculated value for the stress is that. Which of the following figures is correct for the heading in the student's table and the value of the stress written to 2 sig figs? Okay, so, no, that's not right, is it? Because that's not rounded to 7.3, which it should be. Of course, that's not going to be right either then. We have 730 kPa. No, because that would just be 730. It has to be D, doesn't it? Let's just check it. 7.3 times 10 to the 6 pascals. Yes, that is the same as that. That is correct. 18, bullet is fired at an angle at that speed there. Blah, 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 blah. Oh, okay. So what is the correct expression for the horizontal distance are traveled by the bullet? So we know the speed, the horizontal speed, is going to be equal to 200 times cos 30. If you don't know where I'm getting that from, because triangles are pointless when it comes to trig, you're just wasting time. There's a nice easy rule. Have a look at my easy vectors trick video. Trust me, it works. Don't listen to the haters. So therefore we know that, well, speed equals distance over time, so therefore distance is speed times time, so that's going to be our 200 cos 30 times by the time. So there we go. Looks like the answer is going to be A. Easy. 19. What can be deduced from the diffraction of electrons by graphite atoms? Electrons are EM waves. Rubbish. Electrons can also become photons. Rubbish. Electrons interact with what? It's photoelectric stuff. They show wave-like behavior. I stand corrected. That's the easiest multiple choice question of all time. Okay, A 20. Which of the graphs can be used to determine the impulse of a force from the area under the graph? We know this. It's an FT graph. That's the easiest thing of all time. We know it's going to be C. Easy peasy. Okay, let's go on to the meteor questions then, shall we? 21. Droplets of water drip at a constant rate. Explain how you can deduce that the droplets are accelerating. Well, of course, their separation increases with distance. What a weird question. B. Diagram below shows a trolley loaded onto the back of a truck. Why? That's so weird. The truck suddenly accelerates, so like that. The trolley is observed to remain in the same position relative to the ground. Explain the lack of motion of the trolley in terms of one of Newton's laws of motion. Well, it's not going to be the second law, is it? Because the trolley isn't accelerating. It's not going to be the third law because, well, there's no forces really acting on the trolley. The point is, Oh, I guess, could we use the third law? No, I don't think so. It's going to be the first law. First law, there is no net force acting on trolley. And this is because as wheels can turn, to negate, oh, that's a posh way of saying it. To basically just stop friction doing anything. There's no friction between them and truck. There we go. Therefore, no acceleration. Let's go with that. No acceleration. Okay, right, C, a car starts from time 0. Car travels in a straight line with constant acceleration. Displacement time graph is shown. Use the graph to show the speed of the car at T4 is 10 meters per second. You need to get a ruler. You need to line it up. You draw a tangent. That's a terrible tangent, side shorts. Look, I don't have a ruler, okay? Give me a break. There we go. It has to just touch there, of course, doesn't it? Make yourself a nice triangle and you'll find that the gradient is about that. What does it end up being? Yeah, you'll just find that it ends up being about that. You know how to do that, come on. Okay, the mass of the car is that. Calculate the change of momentum, rate of change of momentum of the car from T to blah, blah, blah. Okay, so we know that the final speed was 10 meters per second. So we can just say change in momentum is equal to mv, or m delta v, because it's just going from 0 to 10. So therefore, it's just going to be that times 10. So just going to be 12,000. And therefore, rate of change of momentum, is going to be that divided by 4 seconds. So therefore, that gives us 3,000. Unit for this, well, rate of change of momentum is the same thing as force, isn't it? So we could say newtons. That'll be the best way to do it, yeah. We could say kilogram meters per second squared, but hey, it is force after all. 22, a student has determined the acceleration of blah. The acceleration is given by that, where d is the initial height of the sphere. The student recalls the following data. Or we have uncertainties. Name the instrument the student should use to measure d. Well, it should be a ruler. Calculate the absolute uncertainty in G. Write your answer to 2 sig figs. Okay, so let's get a value for G first. So we're going to say G is equal to 1.4 squared over 2 lots of D, so 2 times 0.1. So in other words, 1.4 squared divided by 0.2. So that's just times by 5. Oh, I can't do it in my head though. I don't know 1.4 squared. 1.4 squared, I'm just going to say times by 5. Oh, that gives us 9.8. There we go. What a surprise. Cool. So we have a value for G. Now we need to find out the percentage uncertainty. So the percentage uncertainty in D is equal to 0.02, sorry, divided by 0.1, then times that by 100. And so that gives us, well, it's going to be 0.2 divided by 0.1. And so there's just going to be 2%. Percentage uncertainty in V is going to be 0.1 divided by 1.4 times 100. So in other words, 10 divided by 1.4. And I don't know what that is, but 10 divided by 1.4, 7. Let's just go with 7%. 2 sig figs, yeah. Oh, 2 sig figs. Ugh. Okay, 2.0. Okay, well, it doesn't matter too much. 7.1%. Okay, so therefore the percentage uncertainty in this is going to be equal to V squared. So therefore we need to double that. So it's going to be 7.1 plus 7.1. And then we need to add on the percentage uncertainty in D as well, which is 2. So therefore that's going to give us 14.2, 16.2%. Okay, are we sounding about right here? Yeah, there we go. Cool. So we'll go with 16%. And so therefore, all we then have to do is say, therefore, the absolute uncertainty is just going to be that 9.8 times, well, our 16% in a decimal form. So yeah, there is a shortcut way of doing this, but it doesn't matter. There we go, 9.8 times 0.16, and that gives us 1.6 meters per second squared. There we go. So don't forget that when you have a value that's squared, then you have to double the percentage uncertainty cubed, triple it, and so on and so forth. 23, a light emitting diode emits visible light when the PD exceeds a threshold voltage. Describe with the help of a circuit diagram how you would carry out an experiment to accurately determine the threshold voltage of an LED in a brightly lit laboratory. Oh, okay. In a brightly lit laboratory. Yeah, I mean, what? Okay. Well, the first thing you do is you want to get rid of the brightly lit bit. So you want to say turn lights off. That's weird. It's implied that the lights have to be on. No, you have to have the lights off so you can just see it turning on. Okay, so we are going to have a power supply, of course. We could have a variable power supply, but the better thing to do is to have a variable resistor, and then we're going to have our light emitting diode there, and then go back to there, and then of course our voltmeter is going to go across that. So we can say decrease resistance of variable resistor until LED just turns on. Read the voltmeter. There we go. It's only 3 marks, so 1 mark for saying turn lights off, circuit diagram, and then get the voltage. There we go. B, the current in a filament lamp is that. Filament wire has a diameter of that. Number density. Oh, I've gone over it, haven't I? Oh, where's that? Okay, so that is D, and this is N. Calculate the number of electrons passing through the filament in 1 second. Okay, so we'll tell you what. Let's make our own little unit, shall we? So we're looking for E per second. So E's S to the minus 1. We know the charge of an electron is 1.6 times 10 to the minus 19 coulombs per electron, as it were. And we have our current, which is 0.045 coulombs per second. So there we go. You might be tempted to jump straight into drift velocity, but that's for the next question, isn't it? So therefore, how are we going to combine these two units to get electron seconds to the minus 1? Well, of course, it's going to be this way around. We're going to have to do 0.045 coulombs per second, because we need seconds to the minus 1, divided by 1.6 times 10 to the minus 19 coulombs per electron. That means that the electrons ends up on top, so we have electrons per second. And what does that give us? So 0.045 divided by that. It gives us 2.8, let's get 2 sig figs times 10 to the 17 electrons per second. Okay, calculate the mean drift velocity. So we are going to need the equation this time. So I is equal to E N A V. Okay, so we're looking for V, so therefore we're just going to put all of this underneath. So therefore we can say that V is equal to I over E N A. So that's going to be, what was our current? 0.045 divided by all of this nonsense put together. So of course the charge of an electron, and then times that by our number density, which is 6.3 times 10 to the 28, times by the area, which is pi d squared over 4 pi r squared. Let's go with pi r squared, seeing that, you know, we can half that nice and easily. So pi times 0.24, so 0.12. So I'm just going to say 1.2 times 10 to the minus 4. Of course, that has to be squared. I'm not going to bother tidying up powers of 10 there. I could do, but I'm not going to. No, it's not worth it. So pop that all into my calculator. And that gives me 9.9 times 10 to the minus 5. That's my drift velocity, that many meters per second. C, student connects a resistor and a thermistor, blah, blah, blah. Battery has an EMF of 6 volts. Yeah, okay, fine. Student draws the following graph, shows a PD across the thermistor against time t. Explain why V decreases at the start. Okay, so current starts flowing, which causes temperature, because it is all to do with temperature, we know this. Temp of thermistor to increase, and they do the opposite to a piece of wire, filament, whatever. Therefore, its resistance decreases. Therefore, so does its share. Yeah, that's all we have to say. Yeah, They've given a really weird answer in the mark scheme. They talked about current. I don't really want to talk about current. Okay. Use the graph to calculate the resistance of the thermistor at time t. So we have 2.4 volts. So the V of the thermistor is 2.4 volts. And we know that it's 6 volts altogether. So V total is 6 volts. And, well, we can't really deal with that because we need to deal with that resistance, don't we? So what we're going to say is that V of the resistor is therefore going to be 3.6 volts because, of course, it has to be mopping up the rest of that 6 volts. We know that when it comes to potential dividers, we know that V is proportional to R. So therefore, we can say that V of the thermistor over V of the resistor is equal to their R's. We're looking for this, so therefore we can say that RT is just going to be, well, let's just pop it over there, shall we? R. So that's going to be 12 ohms times the PD, so it's just going to be 2.4 volts over 3.6 volts. So let's put that into my calculator. 2.4 divided by 3.6, and that gives me 8. There we go. 8 ohms. Nice, easy one there. Just ratio of voltages equals ratio of resistances for a potential divider. 24 space doesn't exist, but that's fine. We will do questions on it anyway. Floating star in a distant galaxy. We have a wavelength. State why the X-rays and UV radiation from this burst were detected simultaneously. Well, it's because all EM radiation travels at the same speed. What a weird question. Dadoy. Calculate the frequency of the X-rays. Okay, so we know that V is equal to F lambda, therefore F is equal to V over lambda, so that's 3 times 10 to the 8 divided by 2.5 times 10 to the minus 11. And, oh, can I do that in my head? Nah, not really. So we know that minus 11 is going to end up on top, so 8 plus 11, so that gives us 19. So 3 divided by 2.5, that just gives us 1.2. So it's going to be 1.2 times 10 to the 19 hertz. Okay, special detectors on the Earth. At the Earth? On the Earth? Whatever. We used to detect individual X-ray photons. In one type of detector, the interaction of a single X-ray photon with the material of the detector. Oh, okay, this is a photoelectric effect question, really. So that's my wavelength there. The interaction of a single X-ray photon with the material of the detector produce many photons of visible light with that. Huh. Oh, okay. Estimate the number of visible light photons emitted in each interaction. Interesting. Okay, so basically we have this one photon coming in, hitting this detector or whatever, and then it sends out loads of these. So we know that the energy of the photon coming in must equal all of the energy of the photons coming out. So we can just say that, yes, energy is equal to hc over lambda, can't we? I guess we can go with frequency. No, we got wavelengths. Let's go with that. The wavelength of this is 5 times 10 to the minus 7 meters, whereas we had the original wavelength up here was 2.5 times 10 to the minus 11. So because energy is proportional to 1 over lambda, well, we know that the higher the energy means fewer photons. So therefore we can say that number of photons, but when do we get a higher energy? We have it with a lower wavelength. So actually we can say, cutting out the middleman, we can say therefore wavelength and number of photons are proportional to each other. The greater the wavelength, the more photons you'll have produced because they each have less energy. Tell you what, I'm going to call that gamma, why not? So therefore I can say that wavelength of the X-rays over the wavelength of the visible photons is equal to the number of photons for the X-rays divided by number of photons for the visible light. Oh, I should have flipped that on its head, shouldn't I? Yeah. Let's swap that around real quick. So we're looking for this, aren't we? And if we're talking about just one X-ray photon going in, then that becomes 1, so that just disappears. So therefore, this is just going to be equal to the wavelength of the visible light. So that's 5 times 10 to the minus 7 divided by 2.5 times 10 to the minus 11. Oh, we can do this in our heads. So that just ends up being 2, and then plus 11 on top, that just ends up being 4. So the answer is 2 times 10 to the 4, or 20,000. Not a super easy question though, but it is a proportionality question because it's here's the NG of an X-ray, and therefore how many of the visible photons are we going to get if the wavelength is different. 25, sound waves cannot be polarized, but they do show diffraction. Why can sound waves not be polarized? Because like any longitudinal wave, their oscillations are parallel to the direction of energy transfer, or we can say direction of propagation. That's a much nicer word. Oh, Mark Scheme says it's longitudinal. Fine. Lazy bones. Oh man, I've just remembered the new ice cream place that's opened down the road. Man, I'm totally getting one after this. Describe and explain how you could demonstrate the diffraction of sound waves in a laboratory. Oh, I don't know. We have a speaker behind slit. So weird. Yeah, just like all diffraction, we should say size similar to that of wavelength. That's a bit redundant. Size similar to wavelength of sound. Sound will be detected. Sound be detected. Sound will be detected. We say by a microphone or whatever. Even when not in view of speaker. Let's go with that. Stupid question. Light can be refracted. Yeah, we know. Define refractive index of a material. Well, we could of course say that it's sin I over sin R, but that's not going to be good enough. Refractive index, the first definition is, well, it basically tells you how much slower light travels in the medium, doesn't it? So therefore we can say that the refractive index is equal to speed of light in vacuum, because it's always greater than 1, so we know that it has to be speed of light in vacuum on top, over speed of light in medium. So we have refractive index of B is 1.3 times greater than the refractive index of A. What? Okay. Does that really matter? No, I guess it doesn't, does it? No, it doesn't. So fine, so we can just say that that's 1.3 and that's 1. Why not? Wavelength is that, fine. Explain how lambda B compares with lambda A. Well, we know that if it's traveling faster in A, then it's going like this in, but then it's going to bunch up. Explain how it compares with A. Oh gosh, okay, fine, whatever. So frequency must be constant, therefore as V is equal to F lambda, if V decreases for B, you can put C equals F lambda, of course, can you? Therefore, so does lambda. Therefore, lambda B is less than lambda A. Easy. Calculate the angle of refraction when the angle phi is 60 degrees. Okay, so this is 60 degrees. So let's go with Snell's law just as it is, as per usual. So I'm just going to say NA sine theta A, or sine phi, let's go with that, is equal to NB sine theta. We can just say that this is 1, this is 1.3, this is 60 of course, so therefore we can say that sine theta is equal to sine 60 over 1.3. So let's do sine 60 over 1.3 first, and we end up with 0.666, so inverse sine that, and it gives us 41 degrees. Sanity check it, 42 actually. Sanity check it, is it less than 60? Yes. Should it be? Yes. So there we go. Sounds about right. 42. Answer to life, the universe and everything. The angle phi is now varied between 0 and 90. Explain whether or not TIR will be observed. No, as TIR only occurs when N1 is less than N2. Therefore, refraction will always occur. Okay, come on, let's finish this paper off. 26, experimental laboratory, find the density. Okay, this is moments, right? Oh, this looks complicated. Good grief. What? Center of gravity, blah, 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 show that the distances x and y are given by the expression, this nonsense, with g is the acceleration of free fall. Okay, so here's our pivot then, isn't it? And this is pulling down, of course. So I guess therefore we can say that the weight of the rod is of course equal to mg, which is equal to the density times the volume times g, which is equal to the density times the length times the area times g. Okay, so that's where that comes from. Cool. So this is just the weight, and then it's just moments, isn't it? We know that this anti-clockwise moment is going to be equal to this clockwise moment here. Therefore, we can say that Vy is equal to Fx. Therefore, rho Lag y. Oh, actually, they want it in terms of y, don't they? Therefore, y is equal to Fx over W. So that's equal to Fx over all of that nonsense. There we go. Data points shown below are plotted. Fine. I'm going to guess that we're going to have to draw a line of best fit. Whoops. That's better. Draw a straight line of best fit. Yep. Just make sure you got the same number of points both sides. I should have done better, but then again, I don't have a ruler. That's a little bit better. Whatever. Determine the gradient. Oh, you guys know how to find a gradient. You'll find the gradient out to be something like 1.5. And use your answer to determine the density rho of the material. So this graph is y against x. So we know that the gradient is equal to y over x. And we said that's about 1.5. Our equation was, wait, what was it? Y equals Fx over L rho g. So we can just pop the x over the other side there. So therefore we're looking for rho. So let's just, well, I'm going to say that that's gradient, all right? I'm going to call that m. Why not? Oh, this looks a bit messy now, isn't it? Let's write it out again. There we go. We're looking for rho, so therefore swap these two bad boys over. So therefore rho is equal to F over A L G M. So that is 6.8 over the area, which is 6.4 times 10 to the minus 5, times the length, which is 0.9, times G, which is 9.8, times the gradient, which is 1.5. Let's put all this nonsense in the calculator and see what we end up with. So 6.8 divided by 6.4 times 10 to the minus 5, 0.9, 9.8, 1.5, and we end up with 8,000. Yeah, 2 sig figs, 8,000 kilograms per meter cubed, 8,030 to be precise. But let's just put it in standard form. Happy days. There we go. Hope you found this helpful. If you did, please leave a like and join the Discord if you need some extra help. And hey, if you really find it helpful, then hit that super thanks button. It really helps me keep making these past paper videos. If you want to see the rest of the papers, then click on the card and it will take you to the playlist. See you next time.